Welcome back to MechFest. I don't know if it was on video or off video, but I mentioned we'd do 3 activities at least with acetals and thioacetals. I lied. It's 4. This time we're doing a sulfur version. It's still the same chemistry. It's the same mechanism to make the acetal. We're going to do it again. And then we're going to learn that this kind of acetal, with sulfur taking the place of oxygen, has chemistry that the oxygen version of this can't do, that we're illustrating here. And there's some stuff at the end too. Please put an arrow here. I forgot to, it's reaction 3 continued, and I forgot an arrow. And yeah, this is going to be a double, because there's 2 things going on here. There's some synthesis, which is pretty exciting, right here. So we got a new synthesis reaction. Dr. Whitaker really likes it. And then it's something, let's see, the carbonyl's back, look. And it was here, carbonyl aldehyde and aldehyde. And when we were finished, because we did a synthesis, it's now a ketone, but it's really the same carbonyl back, ketane, ketone. And we got a new carbon-carbon bond. And there's this sulfur, which is the same sulfur we started with. So in effect, it's like a protecting group to the carbonyl, but it also introduces some new chemistry here, because I know we're still learning. But if you're not seeing that acid-base chemistry is needed here, then you're really missing the fact there's an H here and there's not the same H here. That's real important, and an H minus is a strong base. So I think we know what to do to get this one started. And I bet somebody's going to tell me the right arrows to get this bond made, because we did that earlier with Grignards and organolithiums and acetylides attacking carbonyls. We've done that. So that's not going to be new. Protonating the O is not going to be new. But at the end, we're going to do what's called hydrolysis. Is the opposite of condensation. We're getting rid of the acetal. And I didn't point it out earlier, but I should have. And I'll make it a useful comparison. Our first acetal was here, and it was a reaction that combined molecule A with molecule B to make a bigger molecule while losing water. What general type of reaction is that? A plus B gives a bigger molecule while you lose a small molecule like water. I like that. She said condensation. It needs to look good. I like this one the best. This reaction here is a condensation. It's going to ruin an arrow. It didn't ruin it. Arrow's still there. So making the hemi into the acetal is a condensation. Let's just make sure we know that every time we do it. Oh, I got to put a quote on this one. You guys are going to tell me why. Technically, this particular one, even though the reaction mechanism was identical to the other condensation, why does this one not qualify technically as a condensation? Yeah, it was intramolecular, so it really didn't get bigger. In fact, it got smaller. But we did bring this end into this end while losing water. That's exactly the same, right? It's not molecule A and molecule B condensing. It condensed with itself. That's all. I have no objection. Call it condensation. And we're going to have a condensation in the second half of this mechanism. The first half, hemiacetal, is an addition, by the way. Do a quick verify on that. Look at this product. The black part is methanol, isn't it? You added methanol, didn't you? That's called addition. So we'll just write it one time here. It doesn't even get a fancy color. Okay. The condensation is so common in organic chemistry, and then in biochemistry, it makes everything that's big. And in biochemistry, a lot of things are big. Okay. So I'm going to ask you near the end of the semester, what kind of reaction made this protein? You're just going to say condensation. You're not even going to think anymore at the end of the semester. All the big molecules are made by condensation. All right, a lot of talk. Didn't get started. Red first. And what is the first step in this one? Activate the carbonyl with the strong acid. What's the second step? Attack the carbonyl with the, I can't say poor nucleophile. It's moderate now. But hey, I want the mechanism to be identical. You might not need as strong an acid to catalyze this one because your nucleophile is better. Don't worry about it. And oh, what's the second step? You're going to squiggle out this H, draw it back here. We're going to get right to the intermediate? Oh, wow. That's phenomenal. Look at this. You got to cover yourself with this, though. And you made sulfate here, didn't you? This is going to be almost like cheating. It's not. What was the third step? Take the H with the sulfate ion, the green H that I drew, right? Just make sure it's not red or blue. And you don't have to tell me what it is. I know if it's not red or blue, it's the third color. Oh, now we got to invest in a pen or something. And yep, she's got her purse open. She's gonna get one. Oh, we've got lots for you here. Here, just pick something nice for yourself. Okay. And that gets us right to the thioacetal, doesn't it? Equilibrium. Addition reaction. And a condensation. No, it doesn't get you to this. No. What am I doing? I got too excited there. Way too excited. I got hemiacetal, right? Hemi before acetal. Hey, what's the prefix hemi mean, everybody? Yeah, like a hemisphere. What's that? That's a half a sphere, right? Anybody drive a large Dodge product around here? Anybody? Nobody? Like a Ram? No. My son-in-law does. He's got a Hemi. Yeah, Dodge, that's their advertising. It's got a Hemi. What does Hemi mean? A hemispherically shaped carburetor. Wow. Okay. Yeah, we don't just do chemistry anymore. And blue. We got this. We got that. And we got a sulfur in purple with CH2 once, CH2 twice, and an SH, and the sulfur lost its H. I don't know. That is I'm just going to say that's a hemithioacetal. Does that work for you? Can you remind me what hemiacetal was without the thio in there? It's a carbon that was simultaneously what two things? Alcohol and ether. In this case, it's simultaneously an alcohol and a thioether. Thio means sulfur's there instead of oxygen. And you got to get rid of that OH, don't you? Just a little reminder, this is the condensation coming up. This is where you're going to kick out the water. So what do you have to do to the OH that's up there? It doesn't have enough H's to leave yet. We protonate in the first step. You made sulfuric acid. I bet we can go to the product. We can guarantee you're going to like it. Oh, same arrow twice. There. So you said protonate, use the sulfuric acid that you just made. You're going to need a sulfuric acid conjugate base later. You're going to have to take that H off that's right here later. So you said protonate first, and then remind me what was second. Want to go back to the previous mech? Yes. You had to make a double bond after you protonated the O, right? So you kick in the lone pair on the, in our case, on our new one, it's going to be a sulfur. And it's going to kick water off. And then the last step is to, oh, we're here, sorry. Yeah, I'll kick water off and then attack. So we got that happening, and then acid base. We're good. So we got sulfur. How'd that happen? It was very dangerous. Yeah, we had very dangerous. I said redraw it, and I didn't even draw the right element. Wow. Okay. So sulfur, the nucleophile, can't attack yet. Oh, we can't go to the product. It's okay. We're learning. We're learning. Tell me what the second step was. We made the double bond just now, correct? Or is that, no, we didn't. That's the second step. We need to make that double bond right here. We didn't do it. Baby blue. And here's why we can't combine the next step. You don't have a pi bond to break. You do not have a pi bond to break. It's an important part of the mechanism, the pi bond breaking, when you attack with the other, the sulfur. So you're stuck. You're not stuck. Just can't. You can't shorten it as much as you wanted to. That's all. It's not stuck at all. So yeah, I guess that was a sign. My struggle with that equilibrium arrow. Should listen. We got a C with a double bond, purple S. 1, 2, 3. Is it 3? It's 2. S H. Now this one we can combine, right? Because that has to go to the full-blown thioacetal, also known as a dithiane. How do you do it? Attack the carbonyl. What am I going to use? The lone pair on the S. That will generate, whoa, not attack the sulfur. I should listen to my student. She said attack the carbonyl. Yeah. And what's after that? Because the sulfur has an H there, and in the product it doesn't have it. So talk to me. Talk to me about how to do it. Yeah, okay, I'll do what she said. She said lose the H using the sulfate, but you're going to have to correct me when I'm done because you're going to lose a point, a full point right here. She actually did say that. She said it before I even did it. She said using a different color. Yeah, you can't do that H until you've made that bond. So first step was attack. Second step, in a new color, baby blue, because you already said so. Here's a sulfate that you made. And you've neutralized your sulfur. And you made your thioacetal. You'd never have to use more than one color, ever. She asked, do you have to use more than one color? The answer is no. So go back to our first mechanism where we didn't use multiple steps and use those mechanisms all the way through. Okay, but really try to embrace it. It saves time and you do eventually start to see the necessary intermediate, even though you're not drawing them. Because you're looking at this and say, I got to get from here to here. So the H has to be lost, but that doesn't happen first. The pKa's don't work. It has to be a sulfonium. So there's a sulfonium before you do the baby blue, right? So it's just acid base after that. And we have a new pKa, but it's not really a new pKa. What does that mean? There's this H here that clearly has to disappear. And it's the H attached to a carbon that's a thioacetal. It's very specific. It has to have all of these pieces, or else you can't say this pKa. In the pKa it's a new pK, but it's not a new pKa because it's a number that we had for the precursor to ilids. You remember the number? It's the same number. 30. So I got a few new 30s. Yeah. So KH can do the job, right? Because it's going to go to 35, H2. Let's show it. K is a spectator, H is an anion, hydride. It's going to grab the old H, put it on that carbon between the sulfurs, and we'll move forward in orange up here. You've got your iso here. That's orange. I want blue. Yeah, we may have to say something to the young ladies out there. 2 carbons. Anion. All right. We're going to pause. I think we're back. I hope we're back. And we are here. We have done what? We're up here. We have an anion. Hey, carbon anions. Great for synthesis, right? Organolithiums, Grignards, acetylides. What else have we seen? Cyanide is a carbon anion, isn't it? Cyanide? Strong nucleophile. It's going to attack what? This is a reaction we've done already, early in 16. Attack the carbon of the carbonyl. Now, I know you want to combine steps. You really do, because you're eager and you've learned new things and you want to show the teacher you know the new things. You cannot get that O- that you just made and protonate it with sulfuric acid like you want to. You can't. They are separated steps. You cannot combine them now because you have to do them separate. When I list them 1, 2, 3, you do them 1, 2, 3. Okay? You couldn't have sulfuric acid present before the nucleophile attacked, or else your nucleophile would be destroyed in an acid-base reaction. Just convince yourself. This would happen first. You do not want this to happen, do you? You can't have sulfuric acid present, can you? No. So you do this step, wait for the end, then add sulfuric acid. So we haven't added sulfuric acid yet. We've made our synthesis, very exciting. We got our O- in purple. And we have 2 more carbons there. I think we have everything we need. And that's pretty much what's going in the box, except acid base has happened. Step 3 is beginning. Sulfuric acid is there. I will redraw it right here. And that gets you into the box. And the 3 continued is going to be in the next video. It's called hydrolysis. But I want you to get this down as I stop the video. and then we'll put this on a new page. Stop share and end.